Hello everyone, we're starting Unit 2. Now this first part of Unit 2 is mostly just history, and it's how did we get from how have we ended with our current understanding of the atom, like what was the path that we took to get there. Now, before we jump into that, let's establish like what is a model. A model is a physical representation, whether that's a drawing or some kind of sculpted item that represents a mental idea, something that we cannot see with our human eyes. Okay. Now, another important thing to note is we have one main force that we deal with in this class, and it is an electrostatic force. It's this simple idea of like what you see with magnets, that opposite charges attract and that like charges repel. Like we're going to see this a lot because of protons and electrons and their charges. Okay, so make sure you're comfortable with that idea. All right, so we're going to start our discussion with John Dalton. Dalton developed this theory where he had a few main ideas, that everything's made up of atoms, that atoms of the same element are exactly alike, that they will join together to form new substances, and those substances, we're going to call them compounds, and there's exact ratios of the different types of atoms. And this rearrangement is called a chemical reaction. And I guess last and probably most importantly, he developed this idea, or it kind of started long before him, but then he kind of solidified it with this theory that atoms are small particles that cannot be created, divided, or destroyed. And so Dalton's theory is the indivisible sphere, meaning that we have these atoms, that they're solids all the way through, and we can't divide them any further. Now, obviously, there were some mistakes there, right? This is just an early understanding back in 1803. And so we had to keep developing this idea. He had some great thoughts, and the aspects of that are absolutely true, as in we still have evidence of them today. But there was a lot of development that happened from there. And the next scientist that we'd like to talk about is J.J. Thomson. He created the cathode ray experiment. And so the way that this cathode ray experiment works is we had electric current come in and interact with a substance that then gave off a beam. Okay, and so this beam, he took and he directed the beam between two charged plates. This one was negatively charged and that one was positively charged. Now, think through this. Remember how we talked about how like charges repel and opposite attract? Because the beam, if the beam was neutral, would have just gone straight through. It wouldn't have interacted. But it turns out that the beam was deflected towards the positive and away from the negative. So it was repelled from this and it was attracted to that. So this beam had to contain negative particles. Okay? So he called these negative I don't think he discovered electrons, but I don't think he named them electrons. Not 100% sure on that. Because these negative particles were later known as electrons. Okay. Now, this was an interesting thought because we had this beam that was emitted by matter, but we know that matter in general is neutral, meaning like your pencil sitting on your desktop now, it's not attracted or repelled from other matter because it's neutral. And so if we have these negative particles contained in matter, then we must have some opposite positive particles to neutral out the negative. And so he developed the plum pudding model. J.J. Thomson said that atoms have this general mass that is positive, and contained within this positive mass, we have little electrons. And so the pudding part of this plum pudding model is this positively charged mass, and then the plums in the plum pudding are the negatively charged electrons. Okay, so we've continued this idea of the atom, and we're saying yes, it is neutral, but we know that it contains negative charges, which means it also has to have positive charges as well. Okay, so after J.J. Thomson, there was then Ernest Rutherford, and Rutherford was interested in this idea of like the positively charged part of these atoms, and so he took small positively charged particles, which are actually alpha particles, and he aimed them at a sheet of gold foil. And then he set up this detector behind the gold foil so he would be able to tell if the alpha particles went through it or were deflected by it or where they ended up. Okay, so this is kind of what we ended with. So we have our alpha particles that are being shot out and then directed at this gold foil, and he wanted to know, are they going to bounce off and go this way, this way, this way? Are they going to go straight through? And it turns out what happened is the majority of the alpha particles went straight through the gold foil. Essentially, they went straight through matter that's composed of atoms. Okay, and he was just floored by this. This was not something that he expected to happen. Okay, so the other side of this that was really, really interesting was that some of these alpha particles were deflected, and not deflected in a small amount, but like significantly deflected. Okay? And so he couldn't figure out this combination. He didn't know, first, am I going to have some interaction with this positive mass, but it's less dense than my alpha particle, so maybe my alpha particle will go through it. But so then he saw most of them go through, but some of them were very much so deflected. And it couldn't have been the electron, because the electron was so much smaller than the alpha particle. It wouldn't cause that kind of deflection. We need something with similar mass to cause that kind of deflection. So this is the ideas that he gained from his experiment. Most of the alpha particles traveled through the foil, and so that means that most of the atom has to be empty space. Some were deflected at small angles, which told us that the nucleus has a positive charge, because like charges repel, right? And so essentially that means this alpha particle came in and it got close to our positive nucleus, and it repelled at not such a severe angle. See, like this one, it repelled because they were both like charges. And then occasionally it would bounce back at this severe angle. And from that, he interpreted that there must be a nucleus in the center that contains most of the mass of the atom, because it would have to be there in order to cause that kind of deflection of an alpha particle. All right, now, so he developed this idea. Like we said, atoms are mostly empty space. He discovered and named proton from this experiment. He said that they were positively charged and found in the center, and we called that the nucleus. And that this attraction from the positive nucleus to the negative electrons held those electrons around our nucleus, making an atom. And his idea was that electrons traveled around the nucleus in random paths. Okay, so obviously, like, there were some problems with this. The first the main one really is if we have these negatively charged electrons like floating or flying around, they're attracted to the positive nucleus. So why don't they just fall into the nucleus? Why do they continue traveling instead of just getting closer, 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 and eventually, falling into the nucleus because of that electrostatic attraction? So then after that, Bohr came along. He wanted essentially to answer that question. And he said electrons have very specific energy levels. And that's what causes them to not fall into the nucleus, because energy-wise, an electron can't exist here or here or here. They can only exist here and here, and so it's impossible for that electron to fall into the nucleus. And so that's where you get the Bohr model from, with these circular, let's see, what did they end up calling these? Yeah, circular energy levels. Okay. And keep in mind, this idea was that lower energy electrons are closer to the nucleus because that's their most stable position, because they're opposite charges, so they're attracted to each other, so they want to be close. And so the further away they are, they'd have to have more energy to be that far away. But that's not always necessarily true. We don't find electrons in these established orbits, but we do see them in specific energy levels. Okay. Okay, so let's pause and take a look at this and what we've learned so far. We know that protons are positive, and they have this P plus symbol, and their charge is positive, and they have mass of 1 atomic mass unit, 1 AMU. And their location is in the nucleus. Neutrons are neutral, so they just have this N. Sometimes I see an N not like that. So they don't have a charge. They also have a mass of 1 atomic mass unit. They are found in the nucleus. Electrons, their symbol is an E negative. They have a negative charge. Now, their mass is so much significantly smaller than the neutron and the proton, we say that in comparison, it is about 0 AMU. It contains mass, but it's so unbelievably small compared to the proton and the neutron. This is found outside the nucleus. All right, so let's continue this discussion. Let's make a quick comparison between Rutherford's model and my Bohr model here. So both of them have nuclei that contain protons and neutrons. Both of them have electrons outside of that nucleus, but we see that for Rutherford's model, they're just flying essentially in random paths around the nucleus. They're contained in the area because of the electrostatic attraction, but there's no set place or path for them. And that's the big difference here with our Bohr model. Bohr says, no, they have very specific energy levels, and due to those energy levels, it will dictate the location, whether they're close to the nuclei or further away from our nucleus. Okay? All right, so when we wrap up this conversation in the next video, we'll finish talking about Bohr, and then we'll talk about Erwin Schrödinger.